Special relativity. Mickelson-Morley experiment according to classical physics. Notice: the derivation of this experiment in this lesson is based on the idea that the movement of Earth relative to the alleged ether and the movement of ether relative to Earth are equivalent motion. In classical physics, the light is assumed to travel at velocity c in a medium called the ether, which is at absolute rest. At time t1, the light is emitted at point a1. The relation between space and time at that point is x1 equals x1 prime plus v times t1 equals d plus v times t1. At time t2, the light reaches point a2. The relation between space and time at that point is x2 equals x2 prime plus v times t2 equals d plus v times t2. The difference in space along x-axis is x2 minus x1 equals v times t2 minus t1. Relative to the ether, the light has traveled a distance c times t2 minus t1. At time t3, the light reaches point m2. From the geometry of triangle A1, A2, M2 we can find the relation, from which we obtain the period of time the light takes to travel from point A1 to point A2. At time t3, the light reaches point A3. The relation between space and time at that point is x3 equals x3 prime plus v times t3 equals d plus v times t3. The difference in space along x-axis between point A3 and point A2 is x3 minus x2 equals v times t3 minus t2. Relative to the ether, the light has traveled a distance c times t3 minus t2. From the geometry of triangle A2, A3, M2, we find the relation using Pythagorean theorem, from which we obtain the period of time the light takes to travel from point A2 to point A3. The total period of time the light takes to travel the path A1, A2, A3 can be found, from which we obtain. We will study the light traveling from mirror M2 to mirror M3 and reflecting back to mirror M2. At time t1, the light is emitted at point B1. The relation between space and time at that point is x1 equals x1 prime plus vt1 equals d plus vt1. At time t2, the light reaches point B2. The relation between space and time at that point is x2 equals x2 prime plus vt2 equals d plus b plus vt2. Notice that the t1 equals t1 capital and that a1 equals b1, but that is not the case for time t2 capital and point b2. The difference in space along x-axis between point b2 and point b1 can be found. x2 minus x1 equals b plus v times t2 minus t1. Relative to the ether, the light has traveled a distance c times t2 minus t1. This distance is equal to x2 minus x1, hence, from which t2 minus t1 equals b over c minus v. We will find the time the light takes to reflect back from mirror M3 to mirror M2. At time t3, the light reaches point B3. The relation between space and time at that point is x3 equals x3 prime plus vt3 equals d plus vt3. The difference in space along x-axis between point B3 and point B2 is the following. Relative to the ether, the light has traveled a distance c times t3 minus t2. This distance is equal to negative x3 minus x2, hence c times t3 minus t2 equals negative x3 minus x2. From which t3 minus t2 equals b over c plus v. The total period of time the light takes to travel the path b1, b2, b3 is delta t2. When the apparatus is at 0 degree. According to classical physics, the time registered relative to the ether frame is the same time registered relative to the Earth frame. The difference in travel time when the light reaches mirror M is delta t 0 degrees equals delta t2 minus delta t1. Since t1 capital equals t1, delta t0 when apparatus is at 0 degree equals t3 capital minus t3. The apparatus will be rotated by 90 degrees. When the apparatus is turned 90 degrees, the arm, A, becomes parallel to the direction of the Earth movement. The time delta t1 will be given by the equation. The time delta t2 at 90 degrees will be given by the equation. The difference in travel time when the light reaches mirror M is delta t at 90 degrees equals delta t2 at 90 degrees minus delta t1 at 90 degrees. The difference between these two times is given by the equation. In 1893, Fitzgerald assumed the contraction of the apparatus arm, which is parallel to the direction of the Earth movement relative to the ether by a factor of square root of 1 minus v squared over c squared. In such case the time delta t 0 degrees will be given by the equation. And the time delta t at 90 degrees apparatus position will be given by the equation. In this case the time difference for delta t at 90 degrees apparatus position minus delta t at 0 degrees apparatus position will be equals 0. According to binomial series, we apply binomial series on the following term and on the following term. Substituting in equation 3, after neglecting the term of order greater than v squared over c squared. Substituting in equation 6 after neglecting the term of order greater than v squared over c squared, we obtain delta t at 90 degrees apparatus position. The predicted shift of interference pattern. When the apparatus is turned from 0 degrees to 90 degrees, the change of time difference should create fringe shift of interference pattern. A shift of n fringes is given by the equation delta equals difference in optical path over lambda. The difference in time delta t at 0 degrees minus delta t at 90 degrees formula. Substituting in the delta fringe shift formula. If A equals B equals L, then delta is given by the equation The velocity of Earth in orbit is 30 km per second. Where c is the speed of light in empty space. The wavelength of light. The length of Mickelson first arm apparatus is L equals 11 meters. Substituting in the fringe shift formula delta. Delta equals 0.367 fringe. This is a fraction of a fringe.